Okay, let me welcome all of you to another session of organic chemistry. Now, in today's session, we are going to start our discussion on chapter 22. Chapter 22 is concerned with the chemistry of Enolate Anions. Specifically, we are going to discuss malonic ester synthesis and acetoacetic ester synthesis. Yeah, bless you. Before we start, a couple of announcements. The next class exam is scheduled for next Tuesday. That is April 8th. And because of that, there will be a review session, online review session on Friday, this coming Friday. That is April 4 at 8 p.m. for those of you who may have the time to join us. So I will send you a reminder for that session on Friday. The reason I want to hold it on Friday is so that I have enough time to process the video and then post in time for you to study for the exam on Tuesday. So for those of you who can join us, so mark your calendar. That is this coming Friday, April 4 at 8 p.m. Also, the homework assignment for this week is our end of chapter questions in chapter 22, and that is due on Sunday, April 6th at 11 p.m. Okay, I've also posted the OWL review session from spring 2013 for chapter 22. That has been posted in Blackboard and also in YouTube. Okay, so you may want to take advantage of those videos. Okay, so now let us start our discussion. Okay, what I want to do today, I know you guys have just taken the quiz. Stop me at about close to 10 minutes to the end of class so we could go over those questions. Okay. Okay, so let us start our discussion on chapter 22, the chemistry of Enolate Anions. Before we start, of course, I want to show you this slide here, which gives you the list of learning outcome objectives. In other words, upon completion of this chapter, you should be able to identify Enolate anions and enols. You should also be able to identify those compounds or molecules that could generate Enolate anions. And then you should be able to use Enolate anions as nucleophiles to form new carbon-carbon bonds. Okay, we are going to do a lot of that in this chapter. So now the question is, what are Enolate anions? As you can see on this slide, Enolate anions are carbon anions of those carbons that are next to a carbonyl group, a carbon-oxygen functional group. In other words, if you take a look at this molecule here, any one of these hydrogen here, if we have a base and we remove this hydrogen as a proton, thereby leaving a pair of electrons to this carbon here, then this becomes an Enolate anion. In other words, Enolate anion could also be considered a conjugate base of this molecule here. So anytime you have a carbon-oxygen bond, you remove the hydrogen on the carbon next to that carbonyl group or carbon-oxygen bond. That ion that you obtain is what we refer to as Enolate anion. And then we call this of course, like I told you earlier, we could also refer to this as a conjugate base. Now, if you have this molecule here, see, I have cyclohexanon. This carbon here we refer to as alpha carbon. That is the carbon that is attached to the carbonyl. The carbon that is next to it, if you want to number these carbons here, starting from the carbonyl, 1, 2, 3, and 4, 5, and 6. This carbon number 3, therefore, we refer to that as a beta carbon, which also means all of the hydrogen that are attached to that carbon will be referred to as beta hydrogen. Similarly, the hydrogen that are attached to the alpha carbon are referred to as alpha hydrogen. Now, this carbon number 4 here, we refer to this as gamma carbon, and that also means all of the hydrogen that are attached to that carbon are referred to as gamma hydrogen. Now, you then want to ask, if we have this reaction here, we want to generate an enolate anion. We have hydroxide, which is a base, reacting with cyclohexanon, and it is going to remove the proton from the alpha carbon of cyclohexanon. Get this. Plus water. Okay, if you take a look at this here, let us look at the pKa value, because we want to call this, we want to say that these alpha hydrogen are acidic. We want to say they are acidic. If we look at the pKa value for all of the hydrogens in this molecule, for this alpha hydrogen here, the pKa value is about 20, and for the beta hydrogen, the pKa value here will be about 40, and here the pKa value for this gamma hydrogen here will be about 50. So therefore, we will say the alpha hydrogen are the most acidic. And why are they the most acidic? The reason why they are the most acidic is because when you generate the conjugate base, this conjugate base is stabilized by resonance. You could draw resonance contribution for this, in which we move the pi electron to here, this electron to form a double bond here. So you can see here, the conjugate base that we obtain from the alpha hydrogen could be stabilized by resonance. And that is why it is more acidic than the other hydrogen on this molecule, because this conjugate base here, this one here, cannot be stabilized by resonance. This one here cannot be stabilized by resonance. Now, what do we do with all of this? You also notice what I've done here. Let me take this out of here. If you compare this, the pKa value for all of the reagents and the reactant in this particular equation I've given you, okay, we have here the pKa value for the hydrogen in water is about 16. Of course, we say the pKa value here. Let me take the rest of this out. The pKa value for this is about 20. Now, so whenever you want to perform an acid-base reaction in organic chemistry, the direction of the reaction goes from the stronger acid to the weaker acid. Okay, you can see the arrow that I've drawn here. In other words, the direction of the equilibrium of this reaction is towards the formation of the cyclohexanol. Okay, and that is because we are going to go from this strong acid here, which is water, to a weaker acid. Now, on the other hand, if we want to draw this equilibrium out to the right, we use a stronger base. Okay. So, for example, using the same molecule here, if we use this base, we call LDA, this is LDA. This is called lithium diisopropylamine, and that is why we have the acronym LDA. So for subsequent reaction, whenever you want to use it, just simply write LDA. Now, if you want to drive the equilibrium of this reaction to the right, we use, this is a strong acid here. I'm sorry, a strong base. So what do we have? We have this. And then we have this here. Let me go ahead and write the structure here. Yes.
When you said in acid-base reaction, you said the direction of what goes from strong acid to weak acid?
Yes.
I didn't hear what you said.
It goes from stronger acid to weaker acid. Okay. Now, if you want to drive this equilibrium to the right, okay, we have this here. Let us take a look at the pKa value again. pKa value for this hydrogen is 20. And for this hydrogen here, which would now be acting as an acid, the pKa value for this is 35. So you can see now this is the stronger acid. This hydrogen here will be the stronger acid, and now this will be the weaker acid. So you can see here, the direction of the equilibrium is more towards from the stronger acid to the weaker acid. So if somebody writes you an equation and say what will be the direction of this reaction, then you need to know the pKa value for the acids. Okay, keep in mind the direction goes from stronger acid to weaker acid. Okay, now we could also use some other bases. Okay, this would be a base. This is the acid here. This is the base. Of course, this is the base, and this will be the acid right here. Okay, in addition to LDA and hydroxide, we could also use some other bases. Other bases for generating Enolate anions. We could use this here, potassium tertiary butoxide, and which will be this molecule here. We could also use ethoxide, which will be this molecule here. This could be sodium ethoxide or potassium ethoxide. We could also use methoxide. This could be sodium methoxide or potassium methoxide. Now the question now is, what do we do with the enolate anion? So far, what I've shown you how to generate enolate anion using bases. We could also use acid to generate enolate anion. But what I want to do, I will show you that at the end of today's discussion with regard to generation of enolate anion using acid catalyzed condition. Okay, so say for example now we take this molecule. And we get this. Get enolate anion. Now we could then use this as a nucleophile. So I guess you guys know where I'm going with this here. We could now use this as a nucleophile. If you dump in bromine, for example, this nucleophile could come here, attack this bromine here, displacing the other bromine atom. And what do we get? So now we get an alpha bromoketone. Okay, alpha bromoketone. We could also use the same nucleophile. We could alkylate the same nucleophile, supposing I have here this nucleophile now could attack this here in an SN2 reaction. So you see where we're going with this. Come here, attack this. And so what are we doing? we are now going to alkylate the alpha carbon. Now, I could take this that molecule, react with step 1, LDA. Now, what LDA will do, because it is a bulky molecule, instead of coming here to abstract this hydrogen here, or to plug this hydrogen here, it will come here to pick this hydrogen. In other words, because of the bulkiness, what we call steric hindrance. Okay, so we then have step 2. We could have an alkylating agent. Keep in mind, in your SN2 reaction will only take place on an alkylating agent in which the leaving group is attached to a primary carbon, a methyl carbon, or sometimes a secondary carbon. Keep that in mind. So then we could do this. And then what do we get? Get this. In other words, there is so much we can't do with the Enolate anion. Notice here, when you have an alkyl group in this position here, in the alpha position, and you use LDA, what the LDA will do is simply remove the hydrogen on this alpha carbon, not on this one here, because of steric hindrance. Okay? And then you do your alkylation, you simply alkylate this carbon here, this other alpha carbon. So the Enolate chemistry could allow us to make a very, very complex molecules, which we are going to do today. Now, before we go further into how do we use the Enolate anion, I want to introduce you to a couple or one reaction that is most important going forward. So I'm going to title this as decarboxylation. Decarboxylation of beta keto carboxylic acid and beta dicarboxylic acid. Now, when we say decarboxylation, what essentially we are saying is we are going to remove carbon dioxide from this molecule. And this is a very important reaction. Supposing we have this. Supposing we have that. And then we have this here. Now this is what I mean by beta keto carboxylic acid. Okay, why do we say beta keto carboxylic acid? If you look at this here, if we number this as the carbonyl 1, 2, and 3. Okay? Now if we use the Greek as symbols, Carbon number 2 will be called alpha carbon. Now, relative to the carbonyl carbon here, this carbon number 3 will be called beta carbon. So that is why we call this a beta keto carboxylic acid. Or let me just go the other way because call this 1, 2, 3. Okay? So therefore, this will be your, relative to the carboxylic acid here, this will be your alpha carbon here. And relative to the carboxylic acid, this will be your beta carbon. And that is why we refer to this as beta keto carboxylic acid. Now what will happen here? If you take this molecule and you apply heat, using this symbol here for heat, what happens? What happens?
You take away the carboxylic acid.
Yes, of course. That's what we're going to do here. Okay, so we do here, let me take these numbers out so we don't confuse ourselves. Okay, so now what happens? Anytime you have a beta keto carboxylic acid, this is what happens. We are going to lose carbon dioxide. This carbon bond will break. Now I have this here. So in essence, we are going to form this. Okay, think of it now that we now have an enolate anion right here. Carbon dioxide is gone. And then we have this proton here that was attached to this oxygen here. Imagine that it's floating around. So you can see why the relevance to enolate anion chemistry here. This proton and this conjugate base will simply get together right now. We end up with this here. Of course, don't forget that we have hydrogen here to start with. There was hydrogen here. Okay? So what does it tell us? Anytime you have a beta keto carboxylic acid and you apply heat, what happens? You form a ketone. You form a ketone. Because you are going to lose carbon dioxide, simply just spitting out carbon dioxide. And this hydrogen here now comes to the alpha position. This is what it is here. Let's give you a couple more examples. We could also do this with an aldehyde, even though we say beta keto acid. Supposing I have this, as long as you have that beta relationship between the carbonyl and the carboxyl group, okay? In relation to the carboxyl group, this is alpha carbon here, and this is beta carbon. Okay, this is an aldehyde. Okay, so if we apply heat, what do we get? What do you think we will get? This comes here. This comes here. Pair of electron comes here. And then what do we get? We now have this. Plus carbon dioxide. And of course, this proton here and the enolate anion they combine to now give you. So what do we get here? Okay, once again we have lost the carbon dioxide. Anytime you have a carbonyl beta to carboxyl group and you apply heat, you're going to lose carbon dioxide. And if you start with a ketone, then you're going to get a ketone. If you're starting with an aldehyde, you're only going to get an aldehyde. Now, supposing we have beta dicarboxylic acid. Supposing we have beta dicarboxylic acid. Okay, beta dicarboxylic acid. So in relation to this here, we say this is the alpha carbon, and in relation to this carboxyl group, this is the beta carbon. So therefore, we refer to this as beta dicarboxylic acid. Okay, so we apply heat. What do we get? If we apply heat to this, what kind of compound do you think we are going to get? Carboxylic acid, exactly. So when you start with a beta dicarboxylic acid, you apply heat, then you are going to get a monocarboxylic acid. Okay. So here, spit out the carbon dioxide. This electron comes here, and this hydrogen will combine with the enolate ion, and then what do we get? We get the carboxylic acid. So we get this plus carbon dioxide. Okay, now we've shown you how to make enolate anion. We've also shown you that if you have beta dicarboxylic acid and you apply heat, you only get monocarboxylic acid. Also, if you have beta ketocarboxylic acid, you apply heat, you only get the ketone. Now let us see how do we use this in synthetic design. Through with this? Okay. The first set of reaction I want to show you is what we refer to as malonic ester synthesis. This molecule here can do better than that. This molecule we call malonate. And the common name for this is malonic ester. If you take malonate, and I come here, by the way, the pKa value for this hydrogen here is about 11, so it's fairly acidic. Now, in organic chemistry, any pKa value that is less than 25, we say that hydrogen is acidic. Anything less than 25, we say that hydrogen is acidic. So you can see here, because of resonance stabilization, these two hydrogens here are very, very acidic. Okay, as organic acids. So if I take this, I take ethoxide. The reason why I want to use ethoxide here, because this ester here is an ethyl ester, so you have a hydroxide in this ester. If I take that, what do I get? I get this. By the way, I will represent the ethyl group as ET. Okay, so the ethyl group is ET from now on. So if you see ET, that means ethyl. To make things easy for ourselves. So I get that. So now you form the enolate of malonic, enolate anion of malonic ester. Now if I now dump in an alkylating agent, say I use this here. Now what do I get? Okay, so I get an alkylated malonic ester. Okay. Now if I now take this, I use some of the chemistry that we've done before. Now I hydrolyze this ester, okay, with dilute acid. Okay, what will happen to the ester? They become carboxylic acid. Now you see where we're going with this, right? You see exactly where we're going. Okay, very good. Now if I just apply heat at this point, see what I will get? Okay, I'm going to lose this as carbon dioxide, right? And this hydrogen here will come to here. And what do I get at the end? I get a carboxylic acid. And in the meantime, I have made a new carbon-carbon bond, extended the carbon chain. Okay? So now what do I have? I have this. So I could ask you, starting from malonic ester, to make this compound here, right? Okay, now, plus carbon dioxide is giving off. Now, let me show you. So therefore, one of these hydrogen here, let me actually, one of these hydrogen here will be this here. Okay? Of course, we lost the carbon dioxide. Okay? So that is very important. Okay, you also notice here, when you lose your carbon dioxide, the hydrogen that is attached to one of the carboxyl group, in this case, will now be attached to the alpha carbon relative to the carboxyl group that is left. Okay, so this process here, going from here, forming the enolate anion, forming the alkylated malonic ester, then forming the dicarboxylic acid, and finally forming this here is what we refer to as malonic ester synthesis. And there is a lot of variation of this reaction. Now, supposing we want to add two alkyl groups. Supposing we want to add two alkyl groups. Okay? The alkylation of malonic ester. Okay, so I could take now I could simply say step 1, ethoxide, and then I would say step 2. What does the step 1 do? Form the enolate anion. Okay. Then step 2, I will add methyl iodide for alkylation. Okay. And then I come back again. I say step 3, ethoxide again. What does that do again? Forming another enolate anion. And then step 4, yes.
What are we trying to make here?
Well, we see what we're trying to make in a minute. Okay? So what have we done? Step 1, enolate anion. Step 2, we did alkylation of this carbon, right? Step 3, enolate anion. Then step 4, we add another alkylating agent, okay? So therefore, what will be the product? What will be the product? So the product will be this. And then we have a methyl here, right? And then on this other side, we have the, right. Okay. Now, all we've done so far, that is not the end of the malonic ester synthesis. To call this malonic ester synthesis, you've got to go all the way to the decarboxylation. Okay, so to do that, what do you need to do next? Hydrolysis. You got to keep in mind the decarboxylation only takes place with the carboxylic acid. So you have to do hydrolysis. You do your hydrolysis, and then what do we get? You get dicarboxylic acid. And then you have this. Okay. And now when you apply heat, okay, one of these carboxylic acid will be gone, right? This hydrogen will now come right here. Okay, so now we get this. That hydrogen is now there. It is coming from here, and then you have this here and this here. So I could give you this compound here. Okay, I'll give you this compound here. Okay, and say provide a synthetic scheme for this compound starting from malonic ester. Now, supposing I also do this, we now have a carboxylic acid. Of course, carbon dioxide is given off here. So we have a carboxylic acid. Supposing I now do DCC and ammonia, and I have this. So from the primary amide plus this here, supposing I tell you, starting with malonic ester, to make this molecule here. Some of you will say, wait a minute, you cannot do that. Malonic ester can only give you carboxylic acid, right? But what I'm simply asking you, after you get your carboxylic acid, you got to do something else with it. In other words, I could take you from the end of the malonic ester synthesis to other places. Okay? So anyway, from here all the way to here, from here to here, from here to here to here, to where you lose your carbon dioxide, that is the end of your malonic ester synthesis. But that does not mean that you could not do something with that product. Okay? Now, supposing I ask you to make this molecule for me. How will you make this? How will you make this molecule here? How will you make this molecule using malonic ester synthesis? How will you make that molecule using malonic ester synthesis? Okay? Let us start, okay? Any suggestion?
How do we get there?
Yes, we want to make this from using malonic ester synthesis. Okay, well, let me help you out here. So we start with keep in mind here, if you have to make this from malonic ester, right? You have to start off by assuming that this is the carbonyl of your carboxylic acid. And then once you finish your malonic ester synthesis, you have to perform additional reaction that gives you this metal ketone. So if this is the carbon of your malonic ester, therefore, that tells us that this carbon here must be your alpha carbon, which is this one here. If that is the case, what kind of alkylating agent are you going to use? What is it? Is it monoalkylation or dialkylation? Is it mono or di? It has to be di, right? In which you have the leaving group on the same molecule. Okay, so what do we do here? Okay, so let us start with this. Step 1, ethoxide, right? Step 2, okay, I say if that is the case, how many carbon do I need here? 1, 2, 3, 4. I need 4 carbon in the alkylating agent. So therefore, that would be this here. Right? Okay. So this here, using an excess of this, you don't really need to say excess. That would be, we just have to assume that is what you are doing. This here, with these two here, okay, the first time you form the enolate ion, displaces this here in an SN2 reaction. So let us do step by step. Okay? So the first one you get is so 1, 2, 3, 4. Right? Now the next step, you do another enolate ion. This time, you come here to remove this hydrogen here. And once you form that enolate ion, that will simply just now displace this one here. So now that will lead you to okay?
So all you do is use the Enolate ion?
Yeah, because the alkylating agent is already in the molecule.
Okay.
Okay, because once you generate the enolate anion, it simply comes here. This will now be an what we call intra molecular SN2 reaction. And once you form this, then what do? You then hydrolyze, right? To get your dicarboxylic acid. You get your dicarboxylic acid, and then let's get this out of the way. I'll bring it back. That's where we want to go. Keep that in mind. Okay? And then what do? Now apply heat, and that gives you this. Now, how do we now get to this? How do we now get to this?
Can you use chloride?
Okay, acid chloride, okay. Do acid chloride, carbonic chloride, right?
Mm-hmm.
And that will give us the acid chloride, right? Okay, then what do you do with that? Okay, acid chloride, you want to get the methyl ketone. Gilman, exactly. Now you do the Gilman. Okay. Now you begin to see the importance of this malonic ester synthesis. Okay. Okay. So now what have we done? We've gone from we use the malonic ester synthesis to actually make this compound. Okay. Once we finish the malonic ester synthesis, of course, carbon dioxide is given off here. Then you do another series of reactions to get to your final product. Okay. So now another very important reaction. We are going to come back to this because I want us to do a lot of problems. The more problems we do on this, the more variation you see of this reaction. Okay, another reaction I want to introduce to you is what we call the acetoacetic ester synthesis. They are very similar. They are very similar, okay, because they also have to deal with formation of enolate anion. Acetoacetic ester synthesis. Okay. This molecule here I'm going to use ET. Okay, we call this ethyl acetate. Okay, well, common name, we call it aceto. Well, you know, the common name is this here, so acetoacetic ester. Okay. Now, if we take that, we see that the acetoacetic ester synthesis and the malonic ester synthesis, they are very similar. The difference is, in one case, in the malonic ester synthesis, you get carboxylic acid. But in the case of acetoacetic ester synthesis, you are going to get a ketone. Okay, so let us see. So we start with, once again, we use the ethoxide as a base because the ester here is an ethyl ester. If you have a methyl ester, then you use methoxide as a base. So step 1, and then step 2, we introduce your alkylating agent. Okay, and so what would be that product? That product would be this here. Keep in mind, this is your acidic hydrogen here, because these two hydrogens here are between these two carbonyls, and they will be stabilized by resonance. These are more acidic than this here. Indeed, the pKa value for this is about, for this here is about 11, whereas this here is about 20. Okay? And that is why the ethoxide will selectively come here to react with this as an acid rather than with this here. Okay, so now you have this. And then we have, let me use a different color for the alkylating agent here. Let's use green. Now you have this here. So you see the acetoacetic ester synthesis and the malonic ester synthesis are basically the same. Now at this point, what do you think we want to do? We want to hydrolyze this to carboxylic acid, to a beta keto carboxylic acid. And therefore we get this. Okay, and now what do you want to do at this point? We apply heat. Very good. Okay, once you apply heat, this here will be gone. Carbon dioxide will be gone. Right here will be gone. And this hydrogen here will now come to this carbon right here. Okay, so now what do we get? We get this. That hydrogen is there now, and then this is here. This is there. Okay. So now in the case, so now this here, from here, starting with acetoacetic ester, with the alkylation, with the hydrolysis to carboxylic acid, to the ketone, this is what we refer to as acetoacetic ester synthesis. Of course, you know that carbon dioxide is given off here. Okay, we could also do dialkylation here, right? You could do direct alkylation just as we did with the malonic ester. You can? Okay, so it's about 7 minutes to end of class, so that I want to stop so that we could. You want us to go over the quiz or just continue chapter 22? Okay, you guys could do your nomenclature. That's easy to do. Let's continue this. Huh? I think the majority said let's continue. Majority of one. How many people want to do the nomenclature? You see, that's minority, you see. How many people want to? Yes, that's a minority. Let's continue then. Okay. Huh? Okay, so so this is the acetoacetic ester synthesis. Okay. Now, supposing I ask you this question. Supposing I ask this question, if I give you this molecule here, supposing I ask you, can you make this molecule using the acetoacetic ester synthesis? Just give me yes or no. Can you make this molecule using acetoacetic ester synthesis? Yes. The answer is no. No. No, why? Exactly. Because keep in mind, in the acetoacetic ester synthesis, the alkylation, you need a primary alkylating agent or a secondary alkylating agent. So therefore, if you wanted to use the acetoacetic ester synthesis, this is your alpha carbon. Once you remove you form the enolate. This here, this is a tertiary carbon here. You cannot do an SN2 reaction. So this will not work. So therefore, you cannot make this directly from using acetoacetic. I'm using malonic ester synthesis or acetoacetic ester synthesis. Okay, another question for you. Supposing I have this. Can you make this either from malonic ester synthesis or acetoacetic ester synthesis? So we say this is no. Why? The no is correct. Why? Because after the malonic ester synthesis, this alpha hydrogen here, keep in mind when you lose your carbon dioxide, there must be hydrogen attached to the alpha carbon. Okay, keep that in mind. So now let us now go and do the your homework, the quiz question. You have 5 more minutes. Yes. Okay, so you cannot use this. You cannot also use this because this is you need an SN2. In this case, the alkylating agent will be this. And you cannot use this, cannot use in SN2 reaction. And in this case, this here, the alpha halogen, alpha carbon must contain hydrogen after the synthesis, after the acetoacetic ester synthesis or malonic ester synthesis. Okay, so we are going to continue with this discussion on chapter 22 on Thursday, and also there will be a short quiz on Thursday. And then we are going to finish chapter 22, of course, on Thursday. I want to remind you, the next exam will cover chapters 20, 21, and 22. Okay, so let us briefly go over the quiz. Okay, it should be fairly easy. Trans 3-methyl cyclobutane carbonyl chloride. In this case, okay, this question says provide structures for the following IUPAC names. Okay, so the base name will be cyclobutane carbonyl chloride, and that will be cyclo if you have cyclobutane. Okay, carbonyl chloride. Okay, and then you say trans, so we have to show stereochemistry here. This is carbon 1, carbon 2, and carbon 3. So okay, that means there is a methyl in position number 3, trans. Okay, so that is for this one here. About this here, Z4-hexenoyl chloride. Okay, okay, the base name is contains 6 carbon atom, and therefore Z, that means you have a double bond somewhere in the 4th position. So let us say we have this Z carbon-carbon double bond. Z means that those the hydrogen are on the same side of the double bond, right? Okay, and 4-hexenone. Okay, so this would be carbon 4. Okay, this is 3, 2. Hexenoyl chloride. Okay, that is a chloride right here. 1, 2, 3, 4, 5, 6. That means there's a methyl here. Okay, it's a Z. Okay. About this one here, cyclopentane carbonyl chloride. Cyclopentane carbonyl chloride, and that would be cyclopentane 5-ring system, carbonyl chloride. About this here, N-dimethyl cyclopropane carboxyamide. Yes. On this one here? This here? This one? Which one? This one? This one here, right? You said it doesn't matter where I put.
He said it doesn't matter where you put the carbon, the double bond O, yeah. Doesn't matter which carbon it's on.
This here?
Number C, yeah, C.
C. Oh, yeah, that's what I'm asking. I said this one here. That's what I'm saying.
Okay.
I said this here, right? Does it matter? It doesn't matter because. Yeah. Okay. Okay. Now N-dimethyl cyclopropane carboxyamide. Okay. In this case, the base name here is cyclopropane. Okay. Carboxyamide. Okay. So therefore, you have 3-member ring. Cyclopropane. You then say carboxyamide, so that means you have an amide, okay? But it also say N-dimethyl, so that means we take off these 2 hydrogens here and we replace with methyl. Those methyl group are attached to the nitrogen. Okay, about E. Okay, let's do a couple more and then we'll call it a day. I think you guys should be able to finish this. E, N-dimethyl 2-butene amide. Okay, the base name here is butene amide. That means you have 4 carbon atoms and a double bond in the 2 position. So we have, and it says E. Okay, so we have two positions, we have amide, so that means we have this here, N dimethyl, okay, this is position 1, 2, 3, and since we are talking about E, so that means this must be here, and the hydrogen will be trans to each other. Okay. Okay. So let us do the second one. Actually, you guys should be able to finish that. No. Okay. How about this here? What about the name for this? The base name for this would be what? Okay, it's be from benzoic acid, right? So benzamide. Very good. So therefore, this would be, you have the metal in the 4 position. This is position 1, 2, 3, 4. So that is our 4 methyl, benz for benzoic acid, benzamide. Yes. Huh? No. It's benzamide comes from benzoic, the corresponding carboxylic acid. Okay. And then you could also use P. You could also use P, methyl benzamide. Yes. Okay. Where the carbonyl group is? No. This molecule here, you got to recognize that this molecule here is benzoic acid. You got to know that. Okay, and this is benzoic acid, and therefore this will be a derivative of benzoic acid. Okay. Let us do one more and then we call it a day. This one here. Okay. Any one of you want to finish with this? When we finish the class, you come and see me. We just finish the problem set. Okay, but for the rest of you, let us do one more. Okay, the base name for this will be what? This carbon 1, 2, 3, and 4. Okay, that will be coming from butanoic acid, so that will become butanamide. Okay, so that is butanamide coming from butanoic acid, and then you have the N-methyl, because methyl is attached to nitrogen, so that becomes N-methyl. Okay, and 3-bromo, butanamide. Okay, so that is the end of today's session, but if you guys want to continue this, I will stay around for another 5 or 10 minutes. Okay, so let me just cut off the recording.